Tenakoto katoa. Good morning, everyone. My name is Maxime, and I'm working at NeSI as a data science engineer at NeSI as a data scientist. And today, I would like you to onboard the NeSI consultancy service ship, and we will sail on the data science seas to see what we have been doing in the last 6 months. But first, first let me introduce you to the crew. So the consultancy service at NeSI is made of 4 people. So Wolfgang Hayek, Chris Scott, Alexander Pletzer, and myself. And we are working with scientists working on the HPC platforms to make their code run better and faster. If you want to get in touch with us, please send us an email at support@nesi.org.nz. Before we get started with what we've done in the space of data science, I'd like to start with some definitions. And probably a lot of you know about this diagram, but in this context, it makes a lot of sense for us because data science is about combining the applied mathematics knowledge, the coding skills, and also the domain knowledge, the expertise. And in our specific case, probably we have most of the coding skills and the mathematical knowledge, but the scientists working with us bring the domain knowledge, and we will not be doing data science if we were not working with them. The first event I want to talk about is a hackathon we organized last spring at ZRC 2020. And the goal was to bring people together around the topic of data science and machine learning in particular. So this machine learning challenge, the goal of this machine learning challenge was to analyze some data set that QuakeCore kindly gave us. And this data set is made of the runtime of their earthquake simulation job that they run on the HPC. And there are a set of parameters like the time and space resolution, and they want to predict how long it will take. So more precisely, they want to upper bound how much time it will take. So actually, they don't waste compute time. And as part of these events, multiple people from New Zealand took part in. There was a lot of discussions about the early data analysis, so what we call EDA. And it was very nice to see how people were sharing knowledge and really doing the data wrestling. But at the end of the day, there was also some modeling and prediction. The best results were obtained by Nick Young from the Center of E-Research at University of Auckland. And he managed to do a very good prediction. What you can see on the figure here is the shaded line is the mean and max prediction for each of the test data sets of the runtime. So well done. We'll talk about Nick a bit later again. Okay, so the first consultancy work I'd like to talk about is a work we did with Nuria Lohani from University of Auckland, and she's working in forecasting influenza-like illness. She has 4 years of data, 3 years of training, and there is 1 year additional years for testing. And what she wanted to do is, as she's developing a brand new model to do this forecasting, she wanted to compare it to some baseline model. And so we help her to use Profit, and Profit is a toolbox for time series analysis and forecasting that has been developed by Facebook. To optimize the model, more specifically the hyperparameters of the model, we employed Bayesian optimization, which in 2 words is just a method to do in very few iterations to try to get the best set of hyperparameters. In addition, if you want to evaluate the performance of your model, you need to do some sort of cross-validation. And in this case, the temporal cross-validation scheme is as you see on the bottom left, is you need to split your data set into a training, which is the past data, and you forecast on the future data, and you gradually increase the amount of past data you will feed into your model. And because we're testing on 1 year of data, and the predictions were done on a weekly basis, this is 50 models that you need to train. Fortunately, we have an HPC at hand, and this is an embarrassingly parallel task. So, well, we just distribute that on many computers, and you get pretty easily a 50-fold acceleration. Aside of this, we also we did a bit of upskilling, training Nuria into using the notebooks on Jupyter Hub and Jupyter Lab instances running on NeSI. Oops, sorry. And the last thing I'd like to comment about is the diagram you see on the bottom right, which is an output from the forecasting model. So sorry for the analysis model from profit, and which decompose the time series into multiple components, the trends over years, and the weekly patterns, and also the yearly pattern. And you can see that on the weekly pattern, there is a small bump on Monday, and that's probably people reporting their illness only on Monday and not on Sunday. Okay, next consultancy. It's a totally different topic. We worked with NeSI people, Abba, Olaf, Stephen, and Nelish, to do some weather prediction. I won't go into the details of this specific topic, but if you're interested in, I'll really encourage you to go to a Friday morning session where Nelish will be presenting this work. So what they wanted to do is basically they wanted to learn a bit more how machine learning could help them in their domain, and for that they were doing a proof of concept, trying to downscale, so to predict localized weather information from some course model. And for this, we used climate station data from NIWA, which is from 1945 to 2017. And as part of this project, there were mini models that has to be tested and compared. So the way we help them is we use the workflow management. Well, we help them to deploy a workflow management system called SnakeMake, which will organize the model fitting and training and scoring and summarizing the whole results. So that's what you can see actually on the graph is the task that needs to be carried out to do this model testing. And every time you see an edge, this is something which depends on the previous input. The cool thing is with this sort of tool, if you want to train one more model, you just need to add a few more edges on the side, and the system will not refit and rescore everything which has already been pre-processed, but only the new bits. And of course, if you change a bit the input data, it will rerun everything which should be changed. The sort of summary figures you get at the end to compare the multiple models were like the one we are actually on screen. And we could compare a bunch of metrics and then start discussion about what are the benefits of some models compared to other models. The next thing we did, and I will talk about Nick Young again. So as part of the hackathon, he won some consultancy hours with us, which was great. And he wanted to get to have a look at the crash analysis system data, which is an open source data set provided by NZTA. Contains about 20 years of data, and each data point is a car crash. It's about 700,000 records. For each car accidents, what you have are the weather conditions and the road features, also which sort of vehicles. So a lot of context around the accident. And so what we did is we had a very exploratory approach to look how the data is made and what we could extract as knowledge, and also if we could transform that into a machine learning task and do some prediction about the crashes. So what you see now on screen are the maps, just the maps of the car crashes, and of course this represents the density of population, but also it represents the network. On the right you see Auckland in particular. You can see the streets, and trust me, if you zoom on the CBD, you can even see the grid, the road network there. So that's quite impressive actually. And in terms of modeling and machine learning, so what we end up trying was to predict the severity of a crash. So given an accident happens, will people that are involved in this accident suffer from severe consequences? So for the prediction, the model are not so good per se, but what they managed to do is to do a probabilistic prediction, which is that when the model says that, okay, there's 80% chance that this accident is bad, then the model is true 80% of the time. Which means that if you use this sort of model, you can do some decision under uncertainty afterwards. The whole code of this project is actually open source and online on GitHub. So if you want to have a look and play with it and provide new inputs, you're more than welcome. Okay, let's talk a bit about deep learning on NeSI. So this project is done with Nathan Russell from the University of Otago, and this project also has a nice presentation on Friday, and I really invite you to go to Nathan's talk if you want to know more details about it. But the way we helped him in this case is Nathan wanted to apply some deep learning toolbox to do segmentation of echography images of Earth. There's this EcoCV toolbox, which is available online and has been published alongside a paper. But the thing is, the code has been probably made online to make people be able to look at how things were done. But the reusability, it needed a bit more work to be reusable, to be used on new data. And also in terms of the underlying code, I mean, it was a bit of old code from TensorFlow, so we need some adaptation and some settings. But once we got the code running on the NeSI GPU, we also had to carry to do a bit of analyze a bit the sensitivity of the model, which means that when you put some data, which is a bit different from what you train the model on, how does it react? And here I'm just showing the worst results, which is like if you flip the input data, well, the segmentation on the bottom left will look nice, but if you put it upside down, that is terrible. And we are still figuring out what are the sort of the sensitivity of the model to other perturbations. Like if you crop the name on top, it may change also a little bit. Okay, the last case study I'd like to talk about is a great collaboration we have with Dr. Matthew McDonnell at University of Auckland, also working at MATAI Institute. And Matthew is working on an eye tracking system to diagnose concussion. So to be more precise, so Matthew is this gentleman on the bottom left, and right now what you can see is wearing some glasses, which has 3 cameras. 2 cameras are actually pointing at the eyes, recording the pupil in real time, and the last camera is pointing forward and records what is in front of the subjects. And the way we helped him with this project is in 2 ways. First way is we help him developing some acquisition code. So he's relying on a very nice open source platform called Pupil Core. But the platform is not doing the stimulus presentation. So we developed this part for him so that he could have some stimuli presented on screen at a very precise times and recording synchronized with the gaze being tracked. The second part of this work, which is still ongoing, is to analyze actually the synchronized data between the gaze and what is shown on screen, and to extract measures from the gaze trajectory. What I'm showing now on this faceted plots, each of the subplot is a different fixation event, which means that we ask the person to look at one point on screen, and at some point the marker jumps to another position, and the person has to do an eye movement to jump to this position and to fix that for a certain amount of time. And so the method here is just trying to find when is this jump, so called a saccade, happening. And if we zoom in, we can see that this model, which is a hidden Markov model on the speeds, does an okay job at delineating the start and stop of this event. So this being said, I'd like to conclude about, okay, what doing data science means for us at the consultancy service. Okay, I could go through this list of bullet points. It could be a bit boring. So actually what I prefer to say is what data science means for us is actually it's bringing people together. I'll truly keep that point about the hackathon. That was a really great experience. It's also being passionate about the research that the scientists allow us to work on with them. And it's a way to empower scientists with new analysis tools and to help them to get the best of the data.